Well, let's go to example problem number 2 here. I'm going to go ahead and clear all that off. So get a clean sheet. Example number 2 says, determine the standard enthalpy of the reaction for the combustion of hydrogen sulfide gas, which proceeds according to the reaction shown below. And in this problem, we actually have our hydrogen sulfide reacting with oxygen to form water and sulfur dioxide. One thing I want you to notice is that we have values, or the values of heat of formation. In other words, these values here were determined from a lab or an experience where we took the elemental components of, say, like for the hydrogen sulfide, we took however many hydrogens was needed plus sulfurs, and we added those heats of enthalpy together to get these values here, which are on your table. Now, you won't have to do that for this type of problem. Later on, we'll do something like that, but for right now, those values will be given to you. One thing I do want you to notice is that you have values for 3 of the 4 things that are given here. You don't have a value for oxygen. There's no value for oxygen in the table. However, in the second example, or the third example here, I did give you a value for oxygen, which happens to be 0. The reason why it's 0 is because anything in its elemental state, like oxygen gas, at room temperature has a heat of formation of 0. In other words, it's already in its elemental state, so there's no amount of energy that's needed to get oxygen into its elemental state. However, with these other things, it does require some energy to get those things formed, and often you will always have values for compounds. Elements, not necessarily, unless they're not in their elemental state. So like, for example, if I were to give you a sample of solid oxygen, which is very, very rare, haven't seen any of that in my lifetime, we would have to give you a value for the heat of formation to make solid oxygen, which means that it would have a negative value because we would lose a lot of energy to allow that gas to become a solid. So that's why you do not see a value for that. Also, when using the equation for this, and it's on your equation sheet, I believe it's the second one, it's the heat of formation, it's the delta H is equal to the sigma, and that's just the sum of the heat of the products minus the sum of, and that's a really bad sigma, the heat of the reactants. So on your equation sheet, you have this, and I want you to start using your equation sheet more and more because it's the same equation sheet that you'll have on the AP exam, and you need to use that as a reference. I don't want you to memorize all these equations and expressions and these constants. That's stuff you don't need to memorize. You just need to know how to use those. And I think what we're doing is we're relying too much on the past knowledge, and we're not knowing, or we're not sure where we can find these equations. And I need you to be looking at your equation sheet more often, and do realize that the left side of the equation sheet, split up into 2 columns, you have your equations on the left, and then on the right you have your definition of the variables and you have your constants. Know what those mean. I would be willing to bet that if you look at the equation sheet, that you're going to be responsible for at least 95% of those things. And you need to know how to use them. You need to know how to work those out. And you need to know what those variables represent. So, that being said, make sure that you can find this equation on your equation sheet. Now again, on your equation sheet, it looks a lot cleaner. So that's what we're going to use. We're going to calculate delta H by taking the sum of the heat of the products, which are these, and I'm going to subtract it from the heat of the reactants. So let's go ahead and do that. I'm going to clear this off here. So what I want to do is I have my delta H, and I'm going to take my products. So I have 2 waters, and my value for water is negative 285.8, and that's kilojoules per mole to show your units. Plus, and again, that's what the sigma represents, the sum of the products, 2 times the sulfur dioxide, which is a negative 296, and that's in kilojoules per mole as well. And so there's all my products. Now I'm going to take it minus the sum of the reactants. Well, again, we have 2 hydrogen sulfides, so that's my multiplier, and that's a negative 20 kilojoules per mole. Now, you do have the option. Even though oxygen's listed there, it has no heat of formation. but it could be, let me scoot this over just a hair, could be 0 kilojoules per mole. If you wanted to list that, okay, so whatever that all adds up to be. And that's bracketed in. Okay, so 2 times negative 285.8 plus 2 times negative 296.8. And that equals a negative 1125, we'll say. And that's kilojoules per mole. Okay? So that's the heat of that reaction. So we take the products minus the reactants on that. All right, let's look at the third example here. Again, same process, except not as many things here. So we'll take the heat of our products. Try this one on your own here. So it equals 2 of those. Actually, pause the video here and try to do this on your own. So we have 2 NO2s, which has a value of 33.84. That's in kilojoules per mole. And that's our only product, so go ahead and add that up. And then we'll do 2 times NO, which has a value of 90.37 kilojoules per mole. And again, I'm going to go ahead and show the oxygen, even though you don't have to. But I probably will, I think, in all my examples. And so close that up. So delta H. Come on, pen, don't let me down here. So 2 times 33.84 minus 90.27. So a negative 113. And again, that's in kilojoules per mole. All right, so no biggies there. Again, when looking at these types of problems, always look at your equation sheet. And it's the sum of the heat of the products minus the sum of the heat of the reactants to get your delta H. All right, number 4. Starting off with our first Hess's law equation. Question from number 4 says, calculate the enthalpy of the following reaction where we have nitrogen reacting with oxygen to form 2 NO2s, or nitrogen dioxides. Question wants to know, how much energy is this going to require? Okay, well, the first thing that we need to realize is these are reaction mechanisms, just like what we talked about in the last topic. So you'll be given some reaction mechanisms, and you must use them all. Now, you don't have to use the reaction mechanisms as they're listed, but these delta H values are pretty important. So if I use, say, this reaction mechanism as is, then my delta H will be a positive 180. If I use this reaction mechanism as is, my delta H value will be a positive 112. However, if I flip either or all of these equations, say I take my equation and I need to flip this and make it a product, and flip this and make it a reactant, now my sign flips and it's a negative 112 kilojoules. So if I flip the equation, I flip the sign on my delta H. And we'll do that here. All right, so what we're trying to do is we're trying to get our mechanisms back to that balanced equation. All right, so here's what we need to do. So, and you don't have to start with the first reaction mechanism. You can start with the second one if you like. But in this case, it's not a big issue. We have nitrogen plus oxygen forms 2 NOs. Now, the first thing I want you to recognize is we do have nitrogen here, we do have oxygen here, but we do not have nitrogen monoxide anywhere in this equation. Since we don't have any nitrogen monoxide in the equation, but we do have nitrogen and oxygen as reactants, probably wouldn't be a bad idea to start with that. Since if I look in the second equation, I don't have any nitrogen in the equation, but I do have some oxygen. So I want to make sure that I have my things lined up in the way that would be desirable for a final balanced equation. So I'm going to take this reaction and write it as is. So nitrogen plus oxygen yields 2 nitrogen monoxides. Come on now, guys, right? And my delta H value for that will be a positive 180. Okay, nothing really exciting there. Okay. Now, looking at the second reaction mechanism, I notice I have two NO2s here. Well, I have two NO2s here, so that means that I probably need to have the NO2s on the product side. So I'm going to flip this equation because I want to get NO2 over here. Also, what I want you to recognize is there's only one oxygen here, and there's two up here. So that means that we probably should make sure that we actually have the right number of oxygens on the respective side here. Okay, so let's go ahead and flip this equation. So I'll have, let's go back to our pen. So I'll have 2 NO plus oxygen, which yields 2 NO2. So that means my delta H will have a value of negative 112 kilojoules. Scoot that on down. Okay, so I have what I'm looking for, and again, I'm trying to get back to this final balanced equation here. So now we have things where we want them. Is there anything that we can cancel out on both sides or eliminate? Probably that's the proper term. We have the two oxygens on the same side of the arrow, so we don't want to cancel that out. Nitrogen only appears on the reactant side. NO2 only appears on the product side, but we do have two NOs on both sides. So we can eliminate those. So what's left is N2 plus O2 yields 2 NO2. Then we get to add up our energies here. So plus 180 minus 112, I believe, is 68 kilojoules. Okay? So that reaction actually has a total energy of 68 kilojoules. All right. Let's clear that off. Let's look at our next problem. Hopefully I have enough room here. I think I do. I may have to write smaller. Actually, I'm going to scoot this guy. Hang on here. I don't know if I can. Oops. Let's do this. Hang on here. Let me go home. I'm going to give myself some room here. Scoot it down. So I'm scooting it down to the next page. All right. So backspace, backspace, backspace. All right. All right. So now I've got a lot more writing room. All right. Looking at this example, it says that I've got nitrogen, two nitrogens. Whoops. Let's go ahead and back and write here. Okay. I've got two nitrogens plus 5 oxygen yields 2 dinitrogen pentaoxides. And the question's wanting to know, how much energy is that? Now, what's really crazy here is we have 3 mechanisms, and we also have a lot of things that have fractional coefficients. Pretty cool stuff here, guys. What I don't want you to do is start freaking out and going, whoa, we have fractional coefficients. Don't ever do that. And what this is, it's the actual reactions for forming these particular items. So like for water, this is our heat of reaction for the formation of water, where we'll have 1 complete hydrogen, 1/2 oxygen, makes 1 water molecule. We started talking about heats of formation the last time we spoke, and we never really got into any great detail over this, but this is our fractional coefficient. We always want to make sure that these values, this delta H, is per mole of whatever it is I'm creating. Now, in some cases, you just may have this value for the heat of reaction for a certain substance. But pretty neat stuff that we're going to be doing here. All right, so what we're looking for is our equation to get back to this. All right, now, you're given 3 reaction mechanisms here. We do not have to start with the first reaction mechanism. And my advice is I wouldn't. I would not start with the first reaction mechanism, because you'll notice that if I look at this, I have hydrogen and I have water, and none of those appear in my balanced equation that I'm looking for here at the end. So 2 of the 3 items don't even appear in this equation. So what I'm going to do is I'm going to hold off. I'm going to have to use it, but I'm going to hold off and come back to that one a little bit later. So I want to start with this reaction mechanism. Now, the one thing that I want to notice is what my reactants and what my products are. looking at this reaction, I'll notice that, yeah, I've got water and nitric acid, and neither of those appear in the balanced equation. However, what is kind of neat here is that if I looked at the oxygen from the first reaction, I have that appearing in two of the mechanisms. So the reason why I skipped that first one is because it appears more than once. However, N2O5 only shows up in one of these mechanisms. If it appeared in more than one, I might be a little hesitant to start with this one, but since that's the only place that N2O5 starts, that's the equation I'm going to start with. So what I want to do is, since N2O5 is actually a product, I'm going to flip this equation. So I'll have two nitric acids on the reactant side, which forms N2O5 plus water. Now, so my delta H value in this case, where's my thing at? Is here it's a negative 76.6. Well, since I flipped it, it's now a positive 76.6, and that's kilojoules per mole. I'm sorry, kilojoules. We'll just leave it at that. All right, so we have our one reaction mechanism taken care of. So if you want to cross that out, that's fine. So let's go to the next reaction mechanism. And what I want you to notice is we have nitrogen, oxygen, hydrogen, which we have nitrogen, oxygen. And this is the one and only time that we actually see nitrogen in any of these problems. So I definitely want to leave that equation as is. Even with the fractions, I'm still okay with that. So I'm going to go ahead and leave it as is. So 1/2. Really, come on now. So 1/2 of nitrogen plus 3/2 oxygen plus 1/2 hydrogen yields HNO3. And this is the reaction to form nitric acid, which is pretty cool. Okay, so that'll give me, since I left it as is, I'm going to leave that sign a negative 174.1, and that's in kilojoules as well. All right, so now that I have the two reaction mechanisms finished and flipped the way that I want them, now I can focus on our first one that we talked about. So what I want to do is I want to look at, okay, water and hydrogen. Hydrogen doesn't appear in the overall balanced equation anywhere. Water's probably the thing I want to focus on more. If I look at my earlier mechanisms that I wrote, I notice that water appears right here. And water does not appear in my balanced equation, so I want to make sure that the water is on the opposite side of this water. So if that water is going to remain there, and it will, then I need to make sure that this equation flips. So I'm going to have water as a reactant, and then I'll put my others back in there. So 1 full hydrogen plus 1/2 oxygen. And my delta H value is a negative 285.8 in the forward direction, but it's a positive 285.8 in the reverse direction, and that's in kilojoules. So now I have my three things that I'm looking for. All right. So now, let's get down to, oh, come on, you can write here for me. So now let's get down to business. All right, so we're trying to get to this equation right here. All right. Is there any way that we can cancel anything out at the moment? I would be very, very hesitant to start canceling any items out yet. I do want you to recognize, though, that and we've got some nitrogen, actually 1/2, and I have 2 nitrogens here. Oxygen, kind of bad because I have oxygen on both sides of the equation here and here. So I've got it here, and I've got it over here. So I've got it in 2 reaction mechanisms, so I don't really want to start with that. I can either start with the nitrogen, but I'd be more comfortable starting with the N2O5. So what I want to do is I want to look at how many I have in the balanced equation, which in this case is 2. So what that means is I get to multiply this mechanism by 2. By multiplying that by 2, that means I'm going to multiply everybody by 2 and also multiply the amount of heat by 2. So I'm going to use my eraser here. I'm going to erase that 2, and I don't have any other values to erase. And I'm going to multiply. I had a 2 there, so now that means I have 4. I now have 2 N2O5s and 2 waters. All right, so that reaction looks okay for the moment. So I have 2 N2O5s, which is good, because I had 2 of them up here. Let me erase that as well. Okay. So now let's focus on some other things. All right. Well, now that I have 4 nitric acids up here and I have 1 here, I need to get rid of nitric acid since it does not show up anywhere in this balanced equation. So how can I get rid of nitric acid on the right side if I have 4 of them on the left side? Hopefully you said multiply everything by 4. And if you said that, I like it. So let's see here. Let's scoot that over just a hair there. Okay, so I'm going to multiply 4 times 1/2 of the nitrogen. So if I take 4 times that, what does that turn into? Hopefully you said a 2, which is very good. If I take 4 times 3/2, that should equal 6. In other words, 4 times 3 is 12, divided by 2 is 6. And then again, 4 times 1/2, erase that. And again, that's a 2. Oops. That's a 2. And then 4 times the nitric acid, looking good. All right, so that means we need to multiply this guy by 4 as well. All right. Man, we got 2 reaction mechanisms looking pretty sharp here. All right, now the last mechanism that I want us to look at is we have 1 water down here, but we have 2 up here. So that probably means since water does not appear in the overall balanced equation, we need to get rid of the water. So let's multiply everything by 2. Actually, erase that. Put that back. So multiply everything by 2, which means I'm going to have 2 waters. Oh, I still want to erase that 4 there. So I have 2 waters, 2 hydrogen, and change that 1/2. Multiply that by 2. Whoops. So 2 times 1/2 equals 1. And yeah, I would show that in this problem. And then erase the 2. So now we've got everybody where we need them to be. All right. Also, let's erase the first 2 up here. Okay. All right. So let's go ahead and cancel out of like terms and bring everybody else down. So, oh, and I forgot to multiply U by 2 as well. Sorry about that. Okay, so now we've got all of our multipliers where they need to be. All right, so who can cancel? Well, we have 4 nitric acids. Actually, let me change the color here. Let's back that up here. Let's change the color. It'll be really cool here. Red. So cancel out the nitrics. Okay. Anybody else can cancel? I see 2 waters on both sides, so let's cancel those. Hydrogen. I see 2 hydrogen ions there. And I do have 1 oxygen here, so that 6 is going to go to a 5. All right, and I believe that's everybody. So bring down everything that remains. So we have 2 N2 plus 5 oxygens, and that's everything on the left. And then we have 2 N2O5. All right, and then we get to multiply everybody and add all those together. And if we type all that in, that equals 28.4. And that's in kilojoules. All right, now, this problem probably would not show up on the multiple choice portion of an AP exam. However, the first one that we worked out, and again, I erased all the information there, I wouldn't be surprised if something like this showed up on the AP exam. That would be a good, fair question to ask and to see if you know or understand Hess's law. And again, what actually took place in these reactions is that we were given a balanced equation, and you were asked to take the mechanisms that were involved in that reaction and rearrange them in such a way that we could cancel out any terms that show up on both sides and end up with our reactants and our ideal products so that we could then solve for delta H. I hope this video has helped out a little bit. As always, if you have any questions, do not hesitate to ask.